hit record now. Now we are live. So, it's with great pleasure today we have Professor Laura Baudis for the Snow Lab seminar series. So Laura got the PhD in experimental particle physics at Heidelberg University. Then she moved to Stanford University for a postdoc and to Florida as an assistant professor, and back to Germany in Aachen as a W3 professorship. And since 2007, she's full professor at University of Zurich in Switzerland. So today she will discuss DARWIN as a next generation observatory for dark matter and neutrino physics. Thank you very much, Laura.
Yeah, thank you very much, Silvia. Yeah, for the invitation. I'm really happy to give this talk, even though I cannot visit, obviously. I haven't been to SNOMAS in a long time, so it will be really fun to visit again. And I see quite a few familiar faces and names. Yes, so I will concentrate on DARWIN and mostly on some of the dark matter and neutrino physics, basically double beta decay. So let me hit play. Let me also make this window. Okay. Right, so in terms of dark matter, I think we all know that we are sort of in the dark regarding this roughly 27% component of the matter and energy component in the universe. I'm showing this plot. Can you see my mouse?
Yes, yes, we can.
My head? Yes, okay. So I'm showing this plot mainly to say that, well, the mass range of possible candidates is really enormous, the same with the cross sections. But for this talk, I will mostly discuss the traditional WIMPs, so roughly 1 GeV to tens of TeV or so, but also what is now mostly called light dark matter, so below 1 GeV, 100 MeV and above, at least for liquid xenon detectors. And I won't really discuss ALPS, dark photons, and so on. So how do we try to detect dark matter, WIMPs, and maybe other particles? So at least for WIMPs, mostly via this elastic scattering of nuclei. So the energy, the energy transfer, momentum transfer is pretty low. You will see, I will discuss what the requirements are of a detector. However, recently, with liquid xenon detectors and others as well, we also have been looking at lighter particles via collisions with electrons in this atomic shell, or also like absorption of these light bosons via the so-called axioelectric or other effects, right? And another effect that allowed us to reduce the thresholds, the effective thresholds, and also to be sensitive to lighter dark matter particles is the detection of this bremsstrahlung from polarized atoms, and also electron emission due to the Migdal effect, which still, however, has to be demonstrated experimentally. So in terms of the interaction cross-section here, mostly for WIMPs versus mass. So as you will see later on, we have this region here that's excluded. So you can go to higher masses. We lose sensitivity because the rate scales roughly with 1 over the mass of the dark matter particle. Obviously, at some point you hit very high cross sections, and then the particles wouldn't even make it to your detector if it's underground. And what I just said before here in the plot, if we like to probe this sub GeV range, then we have this scattering becomes very ineffective, of course, because the mass of your particle is much smaller than the mass of the nucleus. So for nuclear recoils, you have, let's say, electron volt or so energy depositions, which are below the thresholds for most, definitely for the xenon detectors. So that's why we are looking for these other types of signals. So that's about the introduction to dark matter. The other physics that I'm going to discuss is neutrinoless double beta decay in a bit more detail. So some of the open questions in neutrino physics. Now, sorry, I just remember I skipped the first slide, but it's okay. So some of the, because there I mentioned some of the open questions in general in particle physics, but yes, in neutrino physics, some of these open questions, as I'm sure you also know, can be addressed with this neutrinoless double beta decay. So the first question we'd like to answer is the nature of neutrinos. Then also what is the absolute value of the neutrino masses, the mass ordering, and all of this is also connected to this origin of small neutrino masses. So this very rare nuclear decay can only occur if neutrinos have mass and also if they're their own antiparticles. And the observation would mean that the lepton number is violated by 2. Typically, half-lives are larger than 10 to the 24 years. So the nice thing is that the expected signature is a pretty sharp peak at the Q value of the decay here. So you have this continuous spectrum, and then here this peak that obviously is smeared by the energy resolution of your detector. Historically, it was Ettore Majorana who had proposed in 1937 that neutrinos could be their own antiparticles. And then soon in 1939, already the double beta decay without neutrinos was discussed by Wendell-Furry. And the one with neutrinos was discussed before by Maria Göppermeier. Okay, so this is, yeah, I'm showing this here because it turns out the dark matter and in general double beta decay experiments have a lot of things in common. And now the energy scale is different. So if you are talking about nuclear recoils or even electronic recoils, you know, we talk about kV energies or below, while in double beta decay, we select nuclei with high Q values because the decay rate depends very strongly. What we call the phase space depends very strongly on the Q value of the 5th power. For dark matter, we expect, if you look at this differential recoil spectrum, it's pretty boring, right? Rather featureless. There's no distinct signature, at least not in the energy spectrum. While, as I mentioned, for the double beta decay, we have this very clear signature and we know where exactly to look for it. And in both cases, we deal with very, very low event rates. And this also is one of the reasons why these main experimental requirements for the two cases are quite similar. So of course, for dark matter detectors, we need low energy thresholds, you know, large detector masses, ultra low backgrounds, and very good signal versus background discrimination. And very similar for double beta decay detectors, where of course, we also need excellent energy resolution. So the resolution also helps for dark matter detectors, especially if you're looking, you know, for ALPS or peak-like signatures. But in double beta decay experiments, it's crucial because it helps you to discriminate against your ultimate background, which is the background from the 2 neutrino double beta decay, right? And this is just roughly how the rate looks like for dark matter detectors, and here the rate for for double beta decay, but here you have the decay rate. Now, of course, these rates here do not mention any detection efficiencies, and in particular, the way that they're written here, they do not address any backgrounds nor resolution. So coming to backgrounds, what are these? Well, in the ideal case, of course, we always like to keep them below the expected signal. So we say we'd like to operate in the background-free mode. That only means that in your expected signal region, you like to have less than 1 background event for a given exposure, for example. So we have of course the muons and associated showers. We also have cosmogenic activation of materials. Then we have all the natural anthropogenic radioactivity that make gammas, electrons, alphas, neutrons, and so on. But finally, after all these times, we almost, not quite, as you will see, reach the point where neutrinos will be the ultimate background, right? So for dark matter, both coherent elastic neutrino nucleus scattering, but also elastic neutrino electron scattering, while for double beta decay, it's mostly elastic neutrino electron scattering. So at least to me, this is quite amazing because I'm I spent already more than 20 years not detecting dark matter and also not detecting double beta decay. But when we started in the 90s, well, mid-late 90s, at least for me, we couldn't have imagined that we will reach this point. So yes, background reduction, again, I'm sure you're all pretty familiar. We must go deep underground, and at SNOLAB, you're of course very lucky because you're very, very deep. Here, in contrast to where we operate our detectors in Gran Sasso, that's by far not as deep. Then we must avoid also it's not only the fact that the detectors have to be underground, but also the materials shouldn't be above ground for too long. This is just an example when we brought some copper, also some xenon, but I'm showing the copper here because it's more spectacular, to the top of Europe, to the Jungfraujoch, so you can see the spectrum that we measured with our Gator detector in Gran Sasso, the gray here before, and the red one, of course, after 1 year. And copper is well measured. It's also, you can predict very well the cosmogenic activation with codes like Activia, Cosmo, and others. So we use this sort of a benchmark. Well, then we fiducialize. This is a plot, by the way, still from Xenon 100. We use active shields for all, most of the modern detectors. And finally, we put a lot of efforts in selecting low radioactivity materials, but not only with gamma spectroscopy, what is shown here, but also other methods, ICP-MS, and we measure for radon emanation and so on. So we will come to that. Okay, so just very briefly to end this introduction. So what is the experimental status? Well, as I mentioned, we haven't seen any evidence for dark matter particles, at least not via direct detection as far as I know, and also no evidence for double beta decay. So if you look at the left plot here, so I took this from the latest PDG review that was actually just published. So we are probing cross sections here at medium, let's say, WIMP mass is around 30 to 40 GeV. So the cross sections must be below a few times 10 to the minus 47 square centimeters. So this is a cross section on the nucleon. What you can also see is, these are constraints also from a variety of experiments, also at lower WIMP masses here. And then the so-called, well, if you want to call it neutrino floor, that is of course dependent on the material. We will see that later on, but is roughly sketched here. So for double beta decay, again, this figure here is in the PDG, but roughly we are probing half-lives above, well, up to 1.8 times 10 to the 26 years. These are in fact the latest results from Gerda. The paper is about to be submitted, but they were shown at the Neutrino conference. So for germanium-76, and then you can set a limit here on the effective Majorana neutrino mass, roughly between 80 and 180 or so millielectron volt. And you have this range because of the nuclear matrix elements. There's a range of these. Okay. So let's come to DARWIN then. So the DARWIN experiment, the goal is to use a large amount of clean liquid xenon target and then detect ionization and excitation when a particle interacts here. So this is very similar, of course, for all of the noble gases, xenon, argon, neon, and so on. So you form when a particle interacts here in your target, you form these excited molecules, the dimers, they dissociate, and you emit here, in the xenon case, you emit photons at 178 or so nanometers. At the same time, you also produce ionization, and if you don't do anything, then at some point these electrons will recombine, and then you will produce more light. We will see that in TPCs, we are trying to measure to extract these electrons. Now, xenon here, that means the strange one. The concentration in the atmosphere is, of course, is very low. It's only about 87 or so ppb by volume, and this also makes this gas much more expensive than, for example, argon. On the other hand, you can also say it's an asset. It's something that you keep. We keep the xenon in closed loops. And in principle, you can also sell it later on. So it's an investment if you want. So the detection principle for DARWIN will be a two-phase TPC. So we have this volume of xenon, of liquid xenon, and then the gas phase on top. So this is very schematic shown here with two arrays of photosensors. So you detect the prompt scintillation light here, and after some time, the so-called proportional scintillation in the gas, and the time difference will tell you the Z position of an event, and then the distribution of light of this so-called S2 signal in the top PMT array that's very localized will give you the XY position. So that's why we say we have 3D position resolution via these two signals. Then also S2 over S1, for example, what is shown here roughly is S2 versus S1, depends on the particle ID, right? Depends on dE over dx. Further, we can do fiducialization. This is important, as we shall see. Most of the background, at least the external background, comes from the walls of your detector. And equally important is single versus multiple interactions, because both dark matter, double beta decay, these scatters, these interactions are definitely single scatters. So if you can reject multiple interactions, you can reject, a significant fraction of your background. So we have this baseline design. The TPC is a bit larger. I'll show you in a second the ones that we have right now, but it's still not, it's not huge, right? It's 2.6 meter in diameter and 2.6 meter height. So the idea is to have 50 tons in total, where 40 tons are actually here inside of the TPC. So the rest provides passive shielding between the TPC and this inner cryostat. Now, in the baseline scenario, we would have two arrays of PMTs. So we are using so far, at least in 1 ton, N ton, these 3-inch PMTs, low radioactivity PMTs from Hamamatsu. Now for DARWIN, we need quite a large amount, around 1800, at least for us, right? In neutrino physics, this is definitely not a large amount of PMTs. Yeah, it is much, it's more than 3 times the number of PMTs that we have now in N ton. And equally in the baseline design, we have these PTFE reflectors and then the copper field shaping rings to have a uniform drift field. We are designing here this detector not with a stainless steel cryostat, but with titanium like LZ. And also for the shield, we are planning not only for a water Cherenkov shield for muons and muon-induced neutrons, but also for an inner shield with gadolinium doped water, just like in N-ton, that is now under construction, to reduce the background from neutrons coming from the detector materials, what we call radiogenic neutrons. I will show you later on, however, there is quite some R&D on other designs for at least I will show you for the photosensors, but there's also R&D on other designs for the TPC and so on. So the benchmark is of course the XENON legacy at LNGS. So since I've been in XENON since before XENON 10, I have to mention this obviously here. So these are the years when these detectors were or will be operated. The total amount of xenon, the drift region, and then the sensitivity for this cross-sectional nucleons. So we started with xenon 10, where we had 15 centimeters drift, and xenon 100, 30 centimeter drift, finally 96, almost 1 meter, xenon 1 ton, and now this is a xenon N-ton TPC that's already, it's already closed inside a cryostat in Gran Sasso, but we'll have 1.5 meters drift, so that's challenging. While for DARWIN, this will be 2.6 meters, as I mentioned. And obviously these pictures are not to scale. If I make them to scale, then it's just too hard. You won't see xenon 10 basically at all, which would be a pity. So I'm just showing here also the PMTs, because for xenon 10, you see it was really cute, very small detector. We had, well, for 10 and 100, we had these 1-inch square PMTs, and then we moved with xenon 1 ton. So you see here also the top, the bottom array, and for N ton, we moved, as I mentioned, to these 3-inch PMTs from Hamamatsu that, as we shall see, you know, they still provide quite a bit of the background. So it's worth thinking about, you know, other possible photosensors as well, for DARWIN at least. So, okay, what is the background goal, and just roughly the main sources, because we will discuss them in more detail, at least when we talk about the double beta decay. So in terms of the dark matter goal, we'd like to have a so-called background-free exposure for, a background-free region for an exposure of 200 ton years in this, you know, roughly 5 to 40 keV nuclear recoil energy. But in general, the philosophy is that both the electronic and nuclear recoil backgrounds should be limited by neutrino-induced events. And that's, of course, easier to say than to achieve, so it will be quite tough. You know, we will discuss a bit radon in liquid xenon, so the goal will be 0.1 microbecquerel per kilogram, so, you know, factor 60 or so reduction to what we achieved in 1 ton. For natural krypton, the goal is 0.1 ppt, and that was already achieved actually with a krypton distillation column in xenon 100. We will have some backgrounds from you know, from the 2 neutrino decay of 136 xenon. We shall see from 137 xenon, that's neutron capture on 136, from 124 xenon. You know, this is something that this is this double electron capture, but as I mentioned in a second, it can also give you background for other things, like if you do some lines, some peak searches at low energies. Then we'll have the solar neutrinos, the radiogenic neutrons, muon-induced neutrons, and this coherent scattering. Yeah, so I think we will discuss about signals and backgrounds. So some of these are backgrounds for, you know, for some signals, while other components are simply only backgrounds, like the neutrons or the muon-induced neutrons. But as an example, on the right here, this is the electronic recoil background from a simulation of DARWIN at low energies. So here from 0 to, well, low to medium to 1500 keV or 0 to 300 keV. This was for the study on the solar neutrino sensitivity of DARWIN. And what you can see is here that this 2 neutrino background, 2 neutrino from 136 xenon decays is quite significant, right? Then you have the PP neutrinos, then you have, you know, radon and so on. So as I said, we'll look at this later, but what you see here are also these, the KK shell, LL shell, and so on from the 124 double electron capture. So just roughly the physics program, of course, DARWIN is hopefully will be built mainly to directly look for dark matter, but at the same time, you know, we are also studying the sensitivity here to the neutrinoless double beta decay, to low energy solar neutrinos, supernova neutrinos, solar axions, ALPS, and so on. So I will mention a few of these, but as I said, I will mostly go into the detail for the double beta decay. So for direct dark matter detection, now xenon has, I think, 9, right, stable isotopes. These are the ones with the highest abundance in the atmosphere. So of course we can probe spin-independent elastic scattering, also spin-dependent elastic and inelastic scattering, because xenon actually has these 2 nuclei with non-zero nuclear spin, 129 and 131. And I'm showing this plot here that because it doesn't show only DARWIN, but also other experiment that's from this preliminary. Well, the report is not yet public, so that's why I made it preliminary, but it's a report for APEC. You have the committee members here. So basically you can see here the current limits, and then the next generation or the current generation, you know, in construction commissioning of xenon detectors, Panda X, LZ, xenon Anton. You also see here the goal of dark side 20K, and then of the much larger detector. I'm sure you're quite familiar with it, with both of them at SNOLAB, with Argo. And then finally here, the prediction for DARWIN, and these neutrino floors that are somewhat different for argon, germanium, xenon, and so on, okay? Now the assumption for DARWIN for this study here is 30 tons of liquid xenon in the fiducial volume. This rejection here, that must still be improved by a factor of 3 to 4 or so compared to what we achieved at this 13% nuclear recoil acceptance. Okay. However, we are just doing a new study. The paper is not ready yet. Ideally, ideally we'd like to discover or to confirm a discovery of WIMP dark matter, in which case you could do what is called WIMP spectroscopy. So you'd be able to have a region in this parameter space of cross-section versus mass that is bound, or maybe not, depending on the WIMP mass, right? So for lighter, well, or medium mass WIMPs like 20, even 100 GeV or so, you would have you would be able to say with some probability here. So these are the 1 sigma, 2 sigma credible regions. What is the cross section? What is the mass under these assumptions, right, of the astrophysical parameters? However, when you go to larger WIMP masses here, for example, 500 GeV, then this nuclear recoil spectrum depends mostly, well, it depends on the reduced WIMP nucleus mass, and for heavy WIMPs it's mostly the nucleus mass. So then you will only be able to set here a lower limit on the mass. Now for solar neutrinos, so this is a recent study that is on the archive. So you could measure, of course, in real time the neutrino spectrum, the solar neutrino spectrum here, roughly 365 events per ton year from PP neutrinos and 140 events per ton in year from 7 beryllium, under the assumption that we reach the same energy threshold like in xenon 1 ton, that's 1 keV. So, so what is shown here is this survival probability of electron neutrinos versus electron energies and existing measurements. So this survival probability would be measured at this low, of course, at the low energies, and ideally with a much better statistical precision, like for example 0.15, 0.2% after an exposure of 300 ton in years, right? What one can also do is measure the survival probability versus the weak mixing angle. It hasn't been measured yet below 300 keV. On the other hand, this measurement would have larger, the statistical precision, let's say, would be worse than, of course, than higher energy measurements of the weak mixing angle. Right, so before I proceed, just one slide on these coherent neutrino nucleus scatters. So the goal not only of DARWIN, but actually already of the upcoming experiments LZ and xenon N-ton is also to detect solar 8-board neutrinos. And this is a study here that's on the archive for xenon N-ton. So these are the Bohr 8, these are the HEP neutrinos. Now, in principle, you have, of course, a lot of events. However, they're mostly at really low energy. So basically the rate above 4 keV or so is almost negligible. So this is a measurement that probably will be done, or well, most likely will be performed with a so-called S2 only, so with a charge signal only, that allows us to reduce very much the energy threshold, right? On the other hand, we will also be looking for supernova neutrinos. So the advantage of this type of detectors is the fact that you are sensitive to all neutrino flavors, right? And this was a study that's a bit older by Raphael and others. So as an example, you would see about 700 events from a supernova that has, the progenitor has 27 solar masses at a distance of 10 kiloparsec. And we are planning to participate in this news network. Actually, we already participated with xenon N-ton in the sense that we could receive, 1 ton, that we could receive alarms. With N-ton, we are also planning to be able to issue alarms. So, okay, so now double beta decay in DARWIN. You may know that 136 xenon is an excellent candidate for a double beta emitter. The 2 neutrino decay has, of course, already been measured. Now, the abundance in natural xenon is not very high. It's not like tellurium. but it's still about 9%. And the Q value is reasonably high, around 2.45 MeV. Unfortunately, it's not really above, as we shall see, above the endpoint of natural reactivity. So so we said, okay, we have all of this xenon in Darwin, then the total amount of 136 xenon is about 3.5 tons. So perhaps it makes sense to study the sensitivity, right? The resolution, as I will show you, what is assumed is that we can achieve the same, this is at 1 sigma, as we have demonstrated in 1 ton. That was actually absolutely not optimized for these high energy measurements. And obviously, as I already said, we need this low or ultra low background environment. So for this study, we did a detailed detector model in GEAN4. So we have this titanium cryostat. You can see here the total mass, right? The outer cryostat, inner cryostat, then the instrumented xenon here, and the buffer outside the TPC that I mentioned is not quite 10 tons, 9 tons. Then we have the TPC components where we assume mostly PTFE, titanium for the electron frames, and also copper like we have now for the field shaping rings. And finally, we have the photosensor arrays where especially the electronics, this is composite different materials, okay, but a total of not quite 1 ton. Now, how to select the signal events in liquid xenon. So the electrons will thermalize pretty quickly and within a short distance, so roughly at a millimeter scale. So definitely the double beta will have a so-called single site topology. So what you see here on the right are these 2 electrons back to back, right? This is a simulation. So you have the Y and here the X position, okay? Now, on the other hand, if you have Bremsstrahlung photons, at least above roughly 300 keV, these may travel for distances larger than roughly, let's say, 15 millimeters. And these are then so-called multi-site events. So it was decided that the energy depositions will be spatially grouped using this density-based spatial clustering algorithm. And what this means is that you have a new cluster if the distance to any previous deposition is larger than a certain separation threshold. And this separation threshold was assumed to be 15 millimeters in the simulation, okay? So you can see here, this is an example of a multi-site event. So you have 2 of these clusters separated here by 23 millimeters, okay? And that means that your efficiency for these double beta events will not be 100% because sometimes you are producing these Bremsstrahlung photons and a single site event or a double beta event will be actually classified as a multiple site event. Okay, so this is now the main background component. So we shall see we have this intrinsic background. These will be the Bohr-8 neutrinos, the 137 xenon, the 2 neutrino double beta decay and radon. Then we have the materials, and what you can see here on the right is this background from the material, so what we call external background, for 100 years of Darwin runtime. Hopefully we don't need to run it so long, only in the simulation. And then different fiducial cuts here, this super ellipsoidal cut, so you have 5 tons, 10 tons, and so on, right? In the end, we used 5 tons as I will show you, just because at these high energies, the background from the materials is still pretty relevant. And then for the materials, we assumed measured activities or just upper limits. For example, for the titanium, this was reached by the LZ collaboration. For all the other materials, we used measurements from xenon 1 ton. Before I go to the sensitivity, just one word again on the resolution. So in this type of xenon detectors, you have this anti-correlation here between light and between charge, and then you use a linear combination of the 2 of them in order to improve your resolution with respect to using one signal alone, right? And again, this is data here from xenon 1 ton and this as well. So this is also actually on the archive. So this is here the relative resolution as a function of energy. And since we don't actually have a measurement exactly at the Q value of the decay, here it was interpolated. So it's roughly 0.8% at 1 sigma at Q beta beta in xenon 1 ton. However, in N ton, we have dedicated electronics so that the signals don't actually saturate, that you don't have to do some signal corrections in terms of saturation. And, you know, hopefully that works well, because this is also the plan for Darwin. Okay, so if you look now at this external material background, in this case for 20 tons, not 5 tons, but 20 tons fiducial volume. So this is the rate in the relevant energy region. What you can see here is this, of course, you have this bismuth gamma line that's very close to the Q value, so 2.45 MeV. Then we have this thallium peak, but what's relevant here are these Compton scattered events in the region of interest. You know, this is just the full width half mass around Q beta beta. And then there's also a scandium in the titanium that's cosmogenic that has this gamma 2.66 MeV. Okay, and the same here, but what is shown are the contribution of the different materials like titanium, copper, PTFE, and so on, and then everything combined. Okay. And then also divided by the type of isotope here with different colors. Now, these were the external backgrounds, but what about the internal ones? So for radon, as I said, we have this assumption, and the idea is to reduce it via material selection and also radon distillation. Our colleagues in Mainz, Christian Weinheim and his group, they just installed the new radon distillation column for N ton in Gran Sasso. And we will also do this BPO tagging. Then we have the radon with this assumption, you can see it here. Then we have the solar neutrinos, so the Bohr-8 neutrinos. This is neutrino electron scattering. And then it turns out, so the 2 neutrino double beta decay, and then it turns out that actually the dominant background here, at least for a detector at the Gran Sasso depth, would be this cosmogenic activation of 137 xenon. So I have neutron capture. So first of all, you have so this is in situ activation. You have neutron production via muon interactions in the xenon itself, right? You have this large mass, these 40 tons of xenon, and then some of these neutrons get captured, produce 137 xenon. The half-life is a bit long. You can do some timing, but you know, it's on the longer side with 3.8 minutes. And then you have this decay to cesium 137 with 30 years half-life, right? That then decays to barium. So what is important is basically this beta decay here that will give you this sort of flattish background around the Q value. Okay, radon I mentioned. Now problematic as in this case is this naked beta from the 214 bismuth decay, because with a branching ratio of 19%, of course, no gamma is emitted. On the other hand, we have the 214 polonium. There we have the alpha decay with a pretty short half-life. And again, I'm sure you're familiar, you can do BPO tagging, and we made the assumptions that efficiency is 99.8%, right? So the bismuth peak that I showed before here, this is really the one from the materials, right? Not from radon that is mixed, with a xenon. So in that case, you really have this beta decay. That's a problem. Okay, and now this is already the, so what is shown here is the total rate versus fiducial mass, right? And you can see, obviously, as you go to smaller fiducial masses, the material background decreases, but not as steeply as we are used to for dark matter searches, you know, below 200 keV or so. This is why, in the end, this rather small 5 tons fiducial volume or fiducial mass had to be selected, right? And then you have this 137 xenon, radon, Bohr-8 neutrinos, and the 2 neutrino double beta decay. And this is now just the rate and around the Q value. So you can see again, this is a signal, assumption of a signal at 2 × 10⁻27. Okay. Now you can do a profile likelihood, you can do a simple figure of merit approach or a profile likelihood analysis to determine the half-life sensitivity. And what came out of these studies with these assumptions that I mentioned is that the sensitivity would be roughly 2 × 10⁻27 years for these 5 tons and 10 years of exposure. While of course, this is the sensitivity to set a limit, while the discovery potential would be lower. So yes, it's not really competitive, let's say, with an X or so, but on the other hand, it is competitive with some of the other projects that will be built for double beta decay. And the question is there any room for improvement? So obviously, as you saw, this external background, if you could reduce, especially if you could reduce the reactivity of the PMTs or use silicon PMs and have a cleaner cryostat, then that would make a difference. There are some ideas on how to reduce also the internal background, improve the BPO tagging, the time veto, but also go to a deeper lab. So this is how it would look like if you wouldn't be in Gran Sasso, but for example 4,800 meter watt equivalent, and this would be neutrino dominated. So what is shown here is the half-life sensitivity versus exposure, and this is this baseline scenario that I mentioned before, right? So in the best case, we could reach roughly 6 × 10⁻27 years. And that is, well, yes, that's, so we are here, these are the current sensitivities. So we are covering in this field, this degenerate mass region, and that's it's a very good region to cover, but in the end, we'd like to cover at least this inverted mass ordering scenario, right? Okay, now just, yeah, going a bit away from the physics, but some slides on the project and also on the R&D. So we are now 30 groups from 12 countries. We are working towards a CDR and then a TDR. So this R&D is organized actually in 6 working groups. So detector, including cryostat, TPC, then light and charge sensors and the readout, backgrounds, how to achieve this very low background rates, including radon cryptal removing, material selections, vetoes, then the liquid xenon procurement, storage, purification, cryogenics. So that's becoming very, very challenging for such a large detector, right? So the world production is about 70 tons or so per year. You have to start very early to get at some point this 50 tons, right? Then we are continuing to study the xenon properties, but also ideas how to calibrate such a large detector, because the larger it gets, also the more challenging it becomes. We see this already, of course, now with xenon N-ton. So in terms of the time scale, we had submitted a letter of intent to Gran Sasso that was positively reviewed, and we were invited to come up with a CDR. And now the plan is to have this CDR in 2022. Then about 2 years later, the TDR and engineering studies. So the construction really in Gran Sasso would only start, well, construction at home institutions, but in Gran Sasso actually only around 25 or so after we finish with N-ton, then commissioning and data taking. So this schedule, of course, might seem a bit aggressive, but we have this experience that is always good to take data with a given detector while at the same time design and then construct the next one. That has been working quite well for us. So the collaboration is about 170 members from 30 institutions, Europe, USA, and Asia. So basically the XENON collaboration, but also other groups that are not in XENON. And we had recently 4 groups joined. So University of Alabama with Igor Ostrowski, University of Hamburg, maybe some of you know Bellina, then University of L'Aquila, and I'm of course very proud because Alfredo Ferella is now their associate professor. He was my postdoc, and also University of Naples. This was our last collaboration meeting. Not everybody could make it, but it was still in person. It was in Gran Sasso in December of last year. That was a really nice meeting. The next meeting will be beginning of September, and well, it will not be in person. We had planned to go to Gran Sasso, but while we can work there to some extent, we are not allowed really to have these meetings, and a lot of people would not be able to participate, so it will be virtual. So in terms of the detector prototypes, two large-scale demonstrators are in construction. One in the Z direction basically, and one in XY. These are supported by the ERC grants. I will discuss a little bit what we are doing here with this one, but they also offer test platforms for the entire collaboration. And then we have various TPCs that are operated at collaborating institutions. So yeah, these are just, it's clear, these are CAD drawings. So these are now some pictures. And this is what we built here in Zurich in terms of this prototype to test a 2.6 meter TPC. And this is built at the University of Freiburg, what they call a pancake. So basically they like to test electrodes. So it's really challenging to build, electrodes with 1 meter diameter, 1.4 meter diameter or so, but 2.6, that will be a huge challenge. So this has to be tested, and then also we need to test that we can actually drift electrons over this field, that we can over this distance, that we can apply high voltage, we can purify. So this all looks very nice. However, this cryostat is actually empty still, so there's still quite some work to be done there. We'd like to commission in late 2020. So we have the support structure, we have the gas system. You can see here some pictures. We'll have about 350 to 400 kilograms of xenon. So it's quite a large amount. We have the inner cryostat is actually not assembled yet. We have the cooling tower, all the electrical system and so on. We are just designing actually the high voltage feed through TPC and also purity monitor. Yes, and I think I already mentioned these goals. This first commissioning will be without an actual TPC at the beginning, just to see that everything works, that we have no leaks, that the cooling, the purification, and so on. And then later we will install the detector. So there is one working group that deals with these light and charge sensors and readout. Some groups are studying this hybrid photosensors, some other groups are studying these VUV silicon PMs, although of course the dark count rate is still factor 50 to 100 too high compared to our PMTs. Other groups, they develop cryogenic electronics here, the Abu Dhabi group for silicon PMs, or also these digital silicon PMs. This is being developed at the University of Heidelberg. Then at Weizmann, Amos Breskin and his group, they are looking at these bubble-assisted liquid hold multipliers, though this would clearly not come in time for DARWIN. However, maybe for a future, for an upgrade, or for a future detector. So in what we did here in Zurich, we upgraded our Zurich detector. This is really a very small TPC that we operated for various reasons, but with two 2-inch PMTs. So we replaced the top PMT with this array of, we had in total 16 readout channels. So you can see here some calibration data with an argon 37 source that we produced here at the Paul Scherrer Institute. This is basically the K shell, the 2.82 kV X-ray from the decay. So the correlation here between S2, S1 is not very strong. And this is our position reconstruction with a resolution of about 1 sigma 1.5 millimeters. So we had this top mesh here, and then at the knots you had you had a stronger signal from these electrons. Okay, so this is, I'm not going to say more. There's a lot more R&D by many groups, and actually we will hear about the newest results in 2 weeks from now. But I go to the summary. Yes, so I hope to have been able to show that DARWIN can have an excellent sensitivity in particle astroparticle physics. And due to the low expected event rates, we clearly need large detector masses, these ultra-low backgrounds. And at the same time, we aim for excellent energy resolutions and these low energy thresholds. Right? Now, if you're talking about dark matter and double beta decay, so detectors, you know, some people say, well, you cannot really do both because dark matter detectors are optimized at low energies. You have, you know, the backgrounds look differently while double beta decay at high energies. But the question is, of course, can we do both? Such a large detector is also not directly cheap, and ideally you like to have a sensitivity that, you know, that allows you to study for various signals, you know, not only actually dark matter and double beta decay, but maybe also solar axions, maybe ALPS, and so on. Eventually, this is limited by neutrino interactions, but these also present new physics opportunities. I only talked very briefly about a few of them. And, you know, you never know what's a background, what's a signal. Perhaps also we remember that yesterday's backgrounds might also be today's signal, who knows. So thanks a lot.
Thank you very much, Laura.
Yeah.
Very nice talk. Fabrice already saved his spot for question.
Okay, I won't use my video. I usually do my exercise during the seminar. So first of all, I would like to thank SNOLAB to let me attend their seminar. This is very nice. So my question now is, you said the silicon PM dark noise is too high for what you want, but you haven't said a whole lot about low mass dark matter, which is, I guess, where it matters the most. But you didn't go very much into capability of the low mass reach. So why is this dark noise a problem if you don't talk about low mass?
Okay, so the dark noise is really a problem if you operate the array at the bottom, right? Where for the S1 signal, like what we did in Zurich, where we only had, I mean, it's not a dark matter detector, but just for a principle, right? The S2 signal is very large. If you have them on the top array, it's not an issue. Now, if you have them on the bottom, the issue is that the rate of accidental coincidences is very high, right? And yes, this is especially an issue if you go to low, you know, to low dark matter, to low energies, right? So what we have seen also in XENON 1-ton studies is that this rate of accidental coincidences really matters at your, you know, rather close to your energy threshold. So we are still looking details into this, but for the current dark count rates that at least we have seen, roughly, if I remember correctly, was 0.8 hertz or so per square millimeter. So for this type of dark count rates, because you have to set the coincident rate to a higher number, you effectively increase your energy threshold, right? So I don't know, instead of getting 5 kV nuclear recoil, maybe you get only 10 or so, and this is not what you want, right? Not even for the standard WIMP, because you have this exponential shape of the nuclear recoil spectrum, right? Of the differential. So I'm not sure if I understood correctly, or.
Yeah, okay. Sure. There may be ways of dealing with, but certainly for single electron and stuff like that, it is overwhelming. I agree. Okay.
I mean, yeah. So now, you know, our Japanese colleagues actually just tested, you know, one of these a new type of MPPC from Hamamatsu with much lower dark count rates. It's not VUV yet, not VUV sensitive yet, right? They put out a paper just, I don't know, a week, 2 weeks ago, maybe. And it seems that Hamamatsu might be working on the VUV sensitive types. We also have, actually, I didn't show this, we also test silicon PMs from FPK. So DarkSide 50, of course, they have, you know, their silicon PMs from FPK, but in argon, you know, you have, it's not such a big issue because on the one hand side, you are colder, right? You're much colder. And on the other side, anyway, you have a somewhat higher threshold because of the pulse shape discrimination that you need. But yes, there's R&D on this, how to decrease actually the dark count rate, indeed, you know, to go into lower fields and so on, right? Yeah.
Okay, thank you.
So next question is Chris.
Thanks very much for a great talk. I'm curious about the dynamic range and the pixelization. So you want pixelization, of course, for your position reconstruction, but if you want to measure from 1 keV to 10 MeV,
Yeah.
or a few MeV, say that's a factor of 10 to the 4, how much dynamic range do you need in each PMT with the amount of pixelization you have? Presumably at
Well,
your very low occupancy.
right. So well, okay. So in xenon 1 ton, our PMTs, you know, they were linear up to they set the signal saturate. It's a bit complicated because we had saturation above already a few hundred kV, but because this was, however, due to the ADC range, right? The base of the PMTs would have been linear, I don't know, up to 1.5 or so MeV, but not up to 3 MeV, right? So that's why we had to do for this analysis to get this resolution, you know, this good resolution at high energies. We had to do some desaturation and so on to model basically the PMT signals at these high energies. For N-ton, what we are doing now, so what we installed, we have these amplifiers, you know, these low noise dual amplifiers, right? So you have one factor 10 amplification like we have in 1 ton, and the other one is de facto 1 amplification, right? That allows you to get this high dynamic range. No? So your initial signal from the PMT will be, you know, will be divided and then amplified. So you split it in 2, then you have to actually amplify it by 20, no? And then by 1. So we will see how this works. But I don't know, was your question more about the actual silicon PMs? Because there we didn't really study it much yet.
No, I was mostly asking about the PMTs and you know, desaturation and what, even if you even needed to do that given the number of pixels you had.
You mean pixels in terms of the number of PMTs?
Right, the light's just distributed by.
Right. Aha, well, yeah, we did. Well, yes, we had to do it because, well, yeah, because the light, you know, they are, so the diameter is, you know, 7.6 centimeters, so they're pretty big. And the light is distributed in some, but not in that many. Yes, I mean, you use the ones where you don't get saturation, so where the signal is not exactly below, but that turned out not to be enough, actually. Yeah. You know, maybe if you have a, as you call it, a pixel, maybe if you would have smaller pixel size, that would work better, of course, right?
Right.
Yeah.
Thank you.
So Nigel is next.
Hi, Laura.
Hi.
So on the
now it's you. Okay. Hi.
On the double beta decay side of things, are there any cosmogenic activation issues that you worry about that you know, might send you to a deeper lab?
Oh yeah, that's so. yeah, exactly. So I mean, you know, you have seen, right? The main background is the cosmogenically produced 137 xenon that you know, you can't really get rid of it because you need it's produced by neutron capture 136, and you need 136, right? And you can do some, as I said, some timing cuts, but you lose a lot because of this long half-life. So really, the most effective is to go to a deeper lab, right? And you know, others have studied this cosmogenic production of the 137, obviously also EXO 200 and EXO, also Kamlanzen. But yes, and EXO will likely not have an issue. Actually, I even have, let me see, I had a slide to compare the numbers. Let's see if I have it here. Not sure if you can see it.
No.
You cannot, sorry, you cannot see, yeah, because I stopped sharing, right? I guess, let's see. Let me just share briefly the screen, yeah.
Now, yes, we can see.
Now, okay. So here I had some comparison. So yeah, we calculated the production, right, in all in all of the materials and so on, but of course it's dominated, so the production of neutrons in all the materials by muons, right? So the production of 137 xenon is dominated by those neutrons coming or being produced directly in the liquid xenon. So we get about 6 or so atoms per ton per year, and this is what an EXO predicts for SNOLAB, right? So 2.2 atoms. But of course, also they have a larger amount, relatively speaking, because they have enriched xenon. No? So in Darwin you have natural xenon. Now Kamlan-Zen, that's a bit of a mystery to me, because at Kamioka, which is not so deep, they actually have this production of 1.42 atoms, so lower actually than an EXO at SNOLAB. Yeah. But I don't know, does it, so this is really the main cosmogenic background. I don't know if it answers your question, Nigel.
Yes, no, that's good, thank you.
So Art is next.
Okay. Hi, Art. Nice to see you again.
Nice to see you. Good, thank you. And good with you, I hope too. Very nice talk, thank you, great summary. For a detector this size, how good a discrimination ratio do you expect to have for high mass WIMPs between electron recoils and nuclear recoils?
Right, right. So I mentioned this only briefly at the beginning. So the assumption now is this, let's see, where did I say it? Well, the assumption is this 90, I think we have 90, did I say it somewhere? So it's roughly factors 3 to 4, what we assume, better than what we achieved, right? So that's another challenge. Let me see, I think
3 or 4 times better than what you have in xenon 1 ton, is that correct?
Exactly, than what we have in xenon 1 ton. I mean, you can increase that number by going to a lower acceptance, but yes, so to get this better discrimination, of course, you also need to improve, your light yield and so on, right?
And so
yeah.
Are those the ways in which you expect to achieve this factor of 3 or 4 improvement?
Yeah, so it's related to the overall light yield. So you have to either to increase the coverage of your photos. Well, you have to increase the coverage somehow. At the same time, you have to increase the quality of the surface of your reflector, like of the PTFE. So we already did some work there in 1 ton in terms of was not perfect, but with diamond polishing and so on. And then, well, we'd also like to hopefully to achieve, roughly a 200 volt per centimeter drift field that we didn't achieve, right, in 1 ton. We had these two science runs, but the main science run, SR1, we had roughly 80 volts per centimeters. Yeah.
So it's not just an objective, it's actually something that's backed up by technical testing that you've already done.
Well, yeah, I mean, in smaller detectors, even better values were already achieved, right? Better is, for example, I think Kaishuan had a detector, but the challenge is really to achieve the discrimination in the large detector in the end. Yeah.
Oh, thank you.
I mean, in the end, you don't do a real counting experiment, right? But still, it's still important, right? The discrimination, indeed. So it's a very good point. Yeah.
Thank you.
I don't see any other raised hand. Are there any other comments or questions for Laura? I have a very naive question. No, wait. No, it was just Nigel in the chat. Can you run both neutrinoless double beta decay and dark matter run at the same time, so the electronic needs to be tweaked in a different way? I mean, can you
yeah. So yes. I mean, the idea would be to run it at the same time. Otherwise, when do you stop the one? Exactly. And again, this is already something that we will be doing for n-ton, right? So with n-ton, as I mentioned, we have these new electronics now, these new amplifiers, so that that we have the high energy signal. Actually, LZ, they also have something similar, right? That the high energy region doesn't saturate. So the measurement is at the same time. I mean, the only thing that you could imagine if, I don't know, you know, you could, let's say after a dark matter run or so, you could think of enriching your xenon not to 90%, but maybe to 40% or to 30% or something, right? And that, of course, it would be done one after the other. But as long as you use natural xenon, you know, I mean, if you're not looking for double beta decay, there are some advantages in using, especially for the PP solar neutrino measurement, in using actually depleted xenon, right? Because then this background, you know, the PP spectrum and the 2 neutrino spectrum, they meet around 30 keV, right? This is when the 2 neutrino spectrum becomes dominant, no? But if that is decreased, then you have a higher statistics measurement, for example, of the PP flux, but also as we showed in that paper, you could also be looking for the CNO neutrinos. And I mean, now they were seen already by Borexino, but still. So yeah, there would be some advantages in having depleted xenon, but that obviously will not allow you to look for double beta decay.
Okay, thanks. Are there any other questions or comments? If not, I would like to sorry for
okay.
Thank you very much.
Clapping in person, that's nice. Yeah. Thanks. Yeah, thanks a lot. Yeah, hopefully, yeah, hopefully you can go back. Well, you are back at the lab, but you said every other week, yes. Right? So yeah, hopefully things will stay like this or improve.
Yes, hopefully.
Yeah. And thanks a lot again for the invitation.
Oh, thank you for accepting.
For the nice questions. Yeah, well, it's sort of easy now, right? You don't have to travel. So
that's true. You know, you lose a bit, but
yeah.